It is the fourth day of the heat wave. At 5:12 in the afternoon, the temperature outside sits at 115 degrees Fahrenheit. The air is so thick and heavy that it distorts the horizon. Down on the streets below the city is operating exactly as it always does. Millions of tourists and residents are moving through perfectly chilled environments, entirely unaware of what is about to happen. Then one single glass tower in the heart of the marina loses power. The buildings right next to it remain brightly lit. The citywide grid has not failed. There is no catastrophic infrastructure collapse across the emirate. Only this specific tower has gone totally dark. 72 floors above the heated pavement, a family sitting in their corner apartment hears the sudden silence. The steady hum of the air conditioning stops. The vents stop pushing cold air, but they do not panic. The apartment is still comfortably cool. The emergency lights in the hallway are already flickering back to life. They look out the window, see the rest of the city shining, and assume this is a momentary glitch, and that absolute faith in the building is exactly why they do not leave. So how much time have they just lost? In the modern era of luxury real estate, especially in a city that attracts over 17 million tourists a year, power outages are barely a memory. The official data from the Dubai Electricity and Water Authority for the year 2025 reported that the average customer experienced less than 1 minute of power loss for the entire year. To be exact, the average was 0.82 minutes. That specific statistic is the anchor keeping everyone inside their apartments. When you live in a city where power never fails, you lose the instinct to flee when it does. You expect the system to correct itself. Down in the mechanical levels of the tower, the emergency diesel generators roar to life. Within seconds, electricity is surging back into the critical arteries of the building. Up on the 72nd floor, the emergency exit signs glow green. The fire alarms remain active. The communication systems in the control room are online. The residents see the lights and breathe a sigh of relief. The crisis they think is already over. But as the family stands near the living room vents, they notice something disturbing. There is no air moving. The lights are on, but the cooling has not returned. Having emergency power does not mean normal life resumes. In this simulation, the backup generators are designed to prioritize survival, not comfort. They must feed the fire safety systems, the exit lighting, and limited rescue functions. What they cannot support is the massive electrical load required to run the apartment cooling systems. The district cooling network might still be pushing chilled water to the building from a central plant, but the internal equipment, the massive air handling units, and the local fan coils required to blow that cold air into the living spaces are dead. The building has power, but it has lost its ability to fight the desert. The family decides to wait for an announcement. The clock moves from 5:12 to 5:32. The apartment is getting warmer. Is the generator saving the building, or is it only keeping the escape route alive? The generator is running exactly as designed. It is doing its job. Dubai has won the battle for emergency safety, but it has instantly sacrificed the ability to inhabit the space. So why is the apartment already losing time? To understand how fast a luxury tower becomes unlivable, we have to look at the glass. Dubai is famous for its towering glass facades. They offer unbroken views of the skyline and the Arabian Gulf. But glass is a highly conductive material. It is a terrible insulator against the brutal Middle Eastern sun. Let us look at a simulation of 3 different apartments inside this exact tower to see which one loses its thermal margin the fastest. Apartment A is located on the 31st floor facing north. It has only one wall of exposed glass, and it receives very little direct afternoon sunlight. Apartment B is located on the 55th floor facing west. It is taking the absolute full force of the late afternoon sun directly through its windows. Apartment C is the family on the 72nd floor. This is a premium corner unit. It has 2 full walls of floor-to-ceiling glass. There are 4 people breathing and generating body heat inside. Natural ventilation is virtually impossible because the windows are sealed for safety and climate control. Which apartment is losing its thermal margin fastest? The answer is the premium corner unit on the 72nd floor. The elements dictating survival right now are solar direction, the surface area of exposed glass, and the ability to vent heat outward. Apartment C has double the glass exposure and 4 internal heat sources. The glass is not the only problem. Glass architecture works beautifully when the massive mechanical systems behind it are working. The danger begins when the sun remains active and the building does not. This reveals a terrifying reality about high-altitude living. A localized power failure does not create one uniform heat trap. It creates hundreds of different localized crises within the exact same building. The people facing north on the lower floors might stay comfortable for hours. The people in the western corner units are watching their ambient temperature rise, degree by degree, every single minute. For the broader tourism and real estate market of Dubai, this is the ultimate hidden vulnerability. The entire luxury economy is built on the promise of absolute climate control. Investors buy these sky-high corner units specifically for the panoramic glass. But without continuous mechanical intervention, the most expensive apartments become the most dangerous environments, the fastest. The apartment losing time fastest is also the apartment farthest from the street. It is now approaching 6 o'clock in the evening. Up on the 72nd floor, the family checks the hallway. The normal elevator service is entirely unavailable. In a power failure simulation of this scale, the standard passenger elevators automatically descend to the ground floor and lock their doors. Only specific service elevators might remain active for emergency responders. The emergency stairwell is illuminated. The concrete steps lead all the way down to the lobby. The family faces a critical choice while their apartment is still relatively safe. Would you leave while the apartment still feels safe, or wait until everyone else reaches the same conclusion? If they leave right now, the stairwell is empty. They have a clear path. Their apartment is warm, but it is not yet suffocating. However, leaving means committing to walking down 72 flights of concrete stairs in the gathering heat. If they decide to wait, they conserve their physical energy. They hold on to the hope that the cooling will restart any minute. But by waiting, they are burning through the easiest window of time they have to escape. They choose to wait. They trust the building. They trust the city. Management has sent a brief automated message saying they are evaluating the switchgear issue. This trust is their second major mistake. As they sit in the living room, the silence becomes oppressive. There is no mechanical white noise. There is only the sound of their own breathing and the occasional distant shift of the building materials, expanding slightly in the heat. Is floor 72 still a luxury address? Or is it 72 floors separating you from relief? The escape route perfectly exists. The stairs are not blocked. There is no fire. There is no structural damage. But the sheer vertical height of the architecture has transformed a simple exit into an extreme physical toll. By 6:15, the family finally realizes the temperature is not going to stabilize. They decide they must prepare to evacuate. They go to the kitchen sink to fill whatever bottles they can find. When they turn the handle, the water flows, but the pressure is noticeably weak. It is little more than a heavy trickle. The building has not lost its entire water supply, but in super tall skyscrapers, water does not simply flow upward by magic. It relies on a series of powerful booster pumps pushing water to different structural zones. In our simulation condition, the upper zone booster pump is not supported by the limited backup power grid. The building still holds water in its pipes, but on the upper floors, reliable pressure now depends on a pump that is no longer running. Cooling was the first essential system to disappear. Water is now becoming uncertain, and every single minute the family spent waiting in denial has made their apartment warmer and the concrete staircase fuller with other panicked residents. It is almost 7 o'clock. The sun is finally touching the horizon. The harsh, blinding light that was baking the western corner of the tower begins to fade into a deep orange glow. Inside the apartment, the family feels a brief psychological lift. They assume that because the sun is disappearing, the aggressive heating of their living space will finally stop. Nighttime in the desert means cooler temperatures, right? But as darkness fully settles over the city, the temperature inside the apartment does not drop. In fact, the air feels heavier. The heat is suffocating. If the sun has gone down, why does the apartment still feel worse? Sunset stopped adding direct sunlight. It did not remove the heat already stored inside the tower. This is the ruthless physics of thermal mass. All day long, the intense solar energy was baking the highly conductive glass. That heat passed through the windows and was absorbed by the concrete floors, the structural pillars, the heavy luxury furniture, and the walls. Now that the outside air is slightly cooling down, all of those materials inside the apartment act like massive thermal batteries. They begin radiating all that stored heat back into the stagnant trapped air of the living space. The desert has stopped attacking the building directly from the outside, but the building is now fighting the massive volume of heat it has already swallowed. The ventilation is sealed. The air is entirely still. The luxury apartment is functioning exactly like a greenhouse in the dark. For the tourism image of a pristine, flawless oasis, this is a nightmare scenario. A structure designed to project ultimate human mastery over nature has just demonstrated that nature always collects its debts. The family can still use the stairs. They have water, even if it is limited. They are young and healthy enough to survive the long walk down. But 4 floors below them, someone cannot. Down on the 68th floor, an elderly resident is sitting in the dark. We are using a composite simulation character to represent a very real demographic vulnerability in high-rise living. This resident has mild respiratory issues and simply does not have the physical capacity to walk down 68 flights of stairs. The temperature in their apartment is approaching 95 degrees Fahrenheit, but the raw temperature is only half the threat. Without the air conditioning constantly pulling moisture out of the air, the humidity from human breathing and the ambient environment is spiking. This introduces the deadly biological metric of the wet bulb temperature. When heat and humidity rise together, the human body loses its primary cooling mechanism. Sweat cannot evaporate into air that is already saturated with water. The body keeps sweating, losing vital fluids, but the internal core temperature does not drop. For an elderly person resting in a stagnant, unventilated room, the physiological strain is building rapidly. Is a tower safe if its escape route only works for people strong enough to use it? The family from the 72nd floor reaches the 68th floor landing in the stairwell. The heavy fire doors are propped open by other residents checking the halls. The family sees the elderly neighbor standing near the doorway looking down into the deep, echoing concrete shaft of the stairs. They face an impossible ethical choice. The family needs to keep moving. The stairwell is incredibly hot. The physical exertion of walking down thousands of steps is already causing their own heart rates to spike. They are generating massive amounts of body heat just by moving. The child asks why they are not bringing the neighbor with them. The parents know the truth. Assisting someone who cannot walk down that many stairs would slow them all down dangerously and expose everyone to prolonged heat exhaustion. They choose to report the exact floor and location of the elderly resident to the building management via a working emergency phone in the stairwell. They leave behind one of their precious bottles of water, and then they begin their descent again. The neighbor must continue to wait for an emergency rescue team that is currently overwhelmed and climbing up from the ground. The emergency evacuation plan works perfectly for the strong. It completely abandons the weak. Through the emergency intercom system in the stairwells, a looped audio message from building management finally plays. Residents able to use the stairs should begin descending. Anyone requiring assistance should report their floor and wait near the protected stairwell. This command officially splits the reality of the tower into two distinct timelines. The descending group is moving deeper into the concrete core of the building. The family from the 72nd floor passes floor 65, then floor 57, then floor 46. The stairwell is completely filled with the sounds of echoing footsteps, heavy breathing, and crying children. The environment inside the stairs is brutal. There is no air circulation. As hundreds of panicking bodies enter the enclosed concrete shaft, they bring their own radiating body heat with them. The temperature inside the escape route is actually higher than in some of the apartments. People are forced to stop on the landings to catch their breath sitting against the warm concrete walls. Small children have to be carried, which doubles the physical exertion for the parents. Their water supply is shrinking fast. Meanwhile, the awaiting assistance group remains trapped in the upper atmosphere. The elderly resident on floor 68 is sitting near the stairwell doors, where the emergency lights cast harsh shadows. A static-filled radio update confirms that a rescue team is en route, but climbing 68 floors in heavy gear takes time. Behind the resident, the apartment continues to bake in the trapped thermal energy of the day. Every minute that passes increases the risk of severe heat illness. Which group is losing time faster, the people moving through the heat or the people conserving energy but remaining upstairs? There is no fire, there is no smoke, there is no stampede, there is no structural collapse. The sheer terror of this simulation comes purely from time, distance, and the fundamental inequality of human physical endurance. The building is successfully evacuating a portion of its population, but it is paying for it with extreme physical suffering, while the most vulnerable residents are left behind to wait in the dark. The family finally reaches the 20th floor. Their legs are shaking. Their clothes are completely soaked in sweat. They have been descending for almost an hour. And then, just as they reach the 19th floor landing, the lights come back. The sudden bright illumination of the main overhead lights causes a wave of cheers to echo up and down the massive concrete stairwell. People stop walking. Some sit down and weep. For the second time tonight, everyone believes the crisis is absolutely over. Down in the lobby, the digital display boards reboot. Main power is restored. Lighting is online. But restoring electricity is not the same thing as restoring a highly complex vertical city. The digital board updates again. Elevators are not released. Apartment cooling is not yet active. When a massive grid connection is re-established, you cannot simply turn everything back on at the exact same millisecond. The massive industrial pumps, the heavy chiller equipment, and the high-speed elevator motors draw enormous amounts of inrush current. If the building automated systems commanded everything to start simultaneously, the surge would trip the main breakers and black out the tower all over again. The systems must return in a carefully timed sequence, and even when the cold water finally begins circulating back into the air handling units on the 72nd floor, the heat stored inside the concrete and furniture does not instantly vanish. It will take hours of continuous high-power mechanical cooling to drag the ambient temperature back down to a comfortable level. The electricity returned instantly. The building could not. Dubai has regained control of the tower, but it is a slow, brutal, and punishing victory. The tower never collapsed. Its deeply reinforced concrete did not crack. Its highly engineered glass panels did not shatter and fall to the streets below. And the city outside the restaurants, the malls, the massive tourist attractions never even lost power. But for several hours this single building remained perfectly upright, while every system that made it livable systematically disappeared around the people trapped inside. What disturbs me is not the possibility that a skyscraper could fall. It is the absolute fact that it does not need to fall to become a trap. The glass itself is not the villain here. The true weakness is the absolute total dependence on invisible machines that must keep working every single minute of the hottest day of the year. A luxury apartment is ultimately just concrete glass and expensive furniture. The machines are what make it habitable. Dubai did not remove the desert heat. It built machines powerful enough to keep that heat outside. So did Dubai actually defeat the desert? Or did it build a vertical city that is never allowed to switch off? This narrative is an illustrative scenario based on architectural thermal dynamics and human physiological responses to extreme heat. It does not represent a specific historical event or a specific structural failure at any named building in Dubai. The performance of infrastructure during a power loss depends entirely on the specific engineering design, backup power configuration, and maintenance protocols of individual properties. If you found this survival simulation eye-opening, make sure to subscribe to the channel and turn on notifications. Leave a comment below telling us what you would have done on the 72nd floor. Would you have taken the stairs immediately or waited for the power to return? Check out our other structural analysis videos on the screen right now to see how modern engineering handles the most extreme environments on Earth. See you in the next one.